You are tuned to Iri-e-learning, and I am your host, Teacher. In this structure and bonding lesson, we will learn to write chemical formulae. Check the description box for links to all the videos related to this unit. By the end of this lesson, we should be able to write chemical formulae for simple ionic and covalent compounds. Let us start with a quick review from previous lessons. So why do atoms bond? Atoms bond or react to form compounds so as to achieve a stable electron configuration. And a stable electron configuration occurs when all the shells of an atom contain their maximum number of electrons. How do atoms achieve a stable electron configuration? Well, they do so by either losing, gaining, or sharing electrons. When an atom loses, gains, or shares one electron, the process requires a lot of energy. Note that an atom will take the route of least energy as it bonds to become stable. We will discuss this point in detail during the lesson. Throughout this lesson, we will be using the term stability number. Therefore, we must understand what the stability number is and how to determine the stability number for atoms, particularly the atoms of the first 20 elements. So what is the stability number of an atom? The stability number is the number of electrons an atom will either lose, gain, or share to achieve a stable electron configuration. We can use the periodic table to assist us in deducing the stability number by following two steps. Step 1, identify the group number. Once we know the group number in which the atom is located, it tells us the number of electrons on the last shell of the atom. Step 2, deduce whether the atom will lose, gain, or share electrons based on its group number. Now, atoms in groups 1, 2, and 3 will lose their valence electrons to become stable. We're going to follow this link for an illustration to show why groups 1, 2, and 3 atoms will lose their electrons to become stable. Say, for example, using an atom from group 1, this atom is sodium, it has 3 shells. We know it's in group 1 because the last shell has only 1 electron on it, and the inner lying shells contain their maximum number of electrons. The first shell contains a maximum of 2 electrons, and the second shell contains a maximum of 8 electrons. Recall that it takes a lot of energy for an atom to lose, gain, or share just 1 electron. Now, an atom in group 1, like sodium, will have 2 options. Either it loses that 1 valence electron to another atom and that last shell would disappear, and leaving behind are the inner lying shells containing their maximum number of electrons. So only 1 electron in this case is moved. Now for the second option, sodium could also gain 7 additional electrons to fill that third shell, which holds a maximum of 8 electrons. Now looking at the 2 options, option 1 involves 1 electron while option 2 involves 7 electrons. The option with the fewer number of electrons will use the least amount of energy. As a result, option 1 is most likely to be the option for atoms with fewer number of electrons on their last shell. They will lose those electrons. Since atoms in group 1 will lose 1 electron to become stable, their stability number is 1. Likewise, atoms in group 2 would lose the 2 valence electrons, leaving behind the inner lying shells with their maximum number of electrons, and as a result, their stability number would be 2. For group 3 elements, they will lose their 3 valence electrons with the inner lying shells remaining with the maximum number of electrons, and because they have lost 3 electrons, their stability number would be 3. Now, groups 4, 5, 6, and 7 will either gain or share electrons to fill the last shell to a maximum of 8 electrons. In other words, it will take the least energy to gain a few electrons to complete the maximum number of electrons on the last shell than to lose the many valence electrons to empty that last shell. So we'll follow our hyperlink just to illustrate what we are saying. So here we have an atom that has 2, 4, 6 electrons on the last shell. So we know that it's in group 6. And this atom is actually phosphorus. And phosphorus has 3 shells. The first shell and the second shell contain their maximum number of electrons. Once again, this atom having 6 electrons on the last shell has the option to lose all those 6 electrons, and the last shell would disappear. So 6 electrons would be lost in this case, and the inner lying shells containing their maximum number of electrons would remain. Or it has the option to gain 2 additional electrons to complete a maximum of 8 on that last shell. Remember that the option involving the least amount of electrons would require the least amount of energy. So that would be option 2. When atoms in group 6 gain 2 electrons to become stable, their stability number is 2. And just to reinforce what we're saying, atoms in groups 1, 2, and 3 will lose all their valence electrons to become stable. And the number of electrons lost is the stability number. So for example, calcium is in group 2. Calcium has 2 electrons on the last shell. It will lose those 2 valence electrons to become stable. Therefore, the stability number of calcium is 2. Aluminium is in group 3. Aluminium has 3 electrons on the last shell. Therefore, it will lose those 3 electrons to become stable, and the stability number of aluminium would be 3. Next, we move on to groups 4, 5, 6, and 7 with a particular focus on the atoms blocked out in green. Now, atoms in groups 4, 5, 6, and 7 will either gain or share electrons to fill the last shell to the maximum of 8 electrons. Notice we have not included group 0 because those atoms are already stable. They already have a stable electron configuration. So for example, chlorine, which is in group 7, so chlorine has 7 electrons on the last shell, and we want to bring that up to a maximum of 8 electrons on its last shell. So we will say the maximum of 8 electrons needed on the shell, subtracting the 7 electrons that are there would tell us how many electrons the atom would need to become stable. So it would need 1 electron to become stable. 7 from 8 gives 1. So as a result, the stability number of chlorine would be 1 because chlorine would either accept or share 1 electron to become stable. Another example is nitrogen. Nitrogen is in group 5, which means it has 5 electrons on the last shell. We find the number of electrons needed for nitrogen to become stable by subtracting the number of electrons on the last shell from the maximum number of electrons that the shell can hold. As a result, the stability number of nitrogen is 3. Nitrogen needs 3 more electrons added to the 5 that's already on the last shell to make the maximum of 8 electrons. We will now start the process of writing simple chemical formulae. The first example is calcium chloride. We begin with identifying the elements in the compound. Calcium is the name of an element on the periodic table, so that is straightforward. On the other hand, chloride isn't found on the periodic table. However, since the name ends with the suffix "ide", this indicates that the atom bonded to form the compound. Therefore, chloride comes from chlorine. Consequently, the atoms of interest are calcium and chlorine. So we will visit the periodic table to obtain the symbols and stability numbers for these 2 atoms. Calcium, symbol Ca, is located in group 2. Therefore, calcium has 2 electrons on the last shell, which it will lose to become stable. Consequently, the stability number of calcium is 2. Chlorine, symbol Cl, is located in group 7. So chlorine has 7 electrons on the last shell. When subtracted from the maximum capacity of 8 electrons for the last shell, the result is 1. Hence, chlorine needs 1 electron to become stable. As a result, the stability number for chlorine is 1. Step 1. Write the symbols of the elements in the compound Ca for calcium and Cl for chlorine. Step 2. Write the stability number to the top right of each symbol. The stability number of calcium is 2 and that of chlorine is 1. Step 3. Cross over the stability numbers to the base of the adjacent element. So 2 goes to the base of chlorine and 1 goes to the base of calcium. The crossed over stability number is now called the base number. If the base number is 1, it is erased and not written in the chemical formula. Therefore, the chemical formula for calcium chloride is CaCl2, where the atoms have bonded in the ratio of 1 calcium, because the symbol of calcium, Ca, means that there's 1 calcium to 2 chlorine atoms. So the base number 2 here indicates 2 chlorine atoms. The second example is aluminium oxide. Oxide indicates the presence of oxygen. Therefore, the atoms of interest are aluminium and oxygen. So let's go to the periodic table to get the symbols and stability numbers for these two atoms. Aluminium symbol Al is located in group 3. Therefore, aluminium has 3 electrons on the last shell, which it loses to become stable. Consequently, the stability number of aluminium is 3. Oxygen symbol O is located in group 6. So oxygen has 6 electrons on the last shell. When subtracted from the maximum capacity of 8 electrons on that last or second shell, the result is 2. Hence, oxygen needs 2 electrons to become stable. As a result, the stability number of oxygen is 2. Step 1, write the symbols of the elements in the compound Al for aluminium and O for oxygen. Step 2, write the stability numbers to the top right of each symbol. The stability number of aluminium is 3 and that of oxygen is 2. Step 3, cross over the stability numbers to the base of the adjacent elements. So 3 goes to the base of oxygen and 2 goes to the base of aluminium. Neither of the base numbers is 1, so the chemical formula for aluminium oxide is Al2O3. The atoms have bonded in the ratio of 2 aluminium atoms to 3 oxygen atoms. It's time to take writing chemical formulae up another notch by introducing what should be done if there is a common factor greater than 1 between the stability numbers of the atoms involved in bonding. For this section, we will start with the example magnesium oxide. So the atoms of interest will be magnesium and oxygen. The suffix "ide" in oxide indicates the presence of oxygen. We will move to the periodic table to get the stability numbers and symbols for these two atoms. Magnesium symbol Mg is located in group 2. Therefore, magnesium has 2 electrons on the last shell, which it loses to become stable. Consequently, the stability number of magnesium is 2. Oxygen symbol O is located in group 6. So oxygen has 6 electrons on the last shell. When subtracted from the maximum capacity of 8 electrons on that last or second shell, the result is 2. Hence, oxygen needs 2 electrons to become stable. As a result, the stability number of oxygen is 2. Step 1, write the symbols of the elements of the compound, Mg for magnesium and O for oxygen. Step 2, write the stability number to the top right of each symbol. The stability number of magnesium is 2 and that of oxygen is 2. So you may have noticed a common factor greater than 1 between the two stability numbers, which takes us to an additional step, step 3, where we divide each stability number by the highest common factor, which is 2 for this example. We then divide the stability number of magnesium by the value of its highest common factor, which is 2, and that would give us 1. The same is done for the stability number of oxygen. We divide by the highest common factor of 2. 2 into 2 goes 1. The final result gives the lowest ratio in which magnesium and oxygen atoms will bond. That brings us to step 4, where the stability numbers are crossed over to the base of the adjacent element. So 1 goes to the base of oxygen and 1 goes to the base of magnesium. If the base number is 1, it is erased and not written in the chemical formula. Therefore, the chemical formula for magnesium oxide is MgO, where the atoms have bonded 1 magnesium atom to 1 oxygen atom. The second example is carbon dioxide. The atoms of interest are carbon and oxygen. The prefix di in carbon dioxide means 2, so the name gives away the fact that there are 2 oxygen atoms present in the compound. However, we will ignore that bit of information and go to the periodic table to get the symbols and stability numbers for carbon and oxygen. Carbon's symbol C is in group 4, so carbon has 4 electrons on the last shell. When subtracted from the maximum capacity of 8 electrons for that last or second shell, the result is 4. Hence, carbon needs 4 electrons to become stable. As a result, the stability number for carbon is 4. Oxygen, symbol O, is located in group 6, so oxygen has 6 electrons on the last shell. When subtracted from the maximum capacity of 8 electrons on that last shell, the result is 2. Hence, oxygen needs 2 electrons to become stable. As a result, the stability number for oxygen is 2. So we will follow the steps. Step 1, write the symbols of the elements in the compound, C for carbon and O for oxygen. Step 2, write the stability numbers to the top right of each symbol. The stability number of carbon is 4 and that of oxygen is 2. You may have noticed a common factor greater than 1 between the two stability numbers. Step 3, divide each stability number by the highest common factor, which is 2 in this example. We then divide the stability number of carbon, which is 4, by the value of the highest common factor, which is 2. This gives 2. The same is done for oxygen. The stability number of 2 is divided by the highest common factor of 2, and this will give us 1. Step 4, cross over the stability numbers to the base of the adjacent elements. So 2 goes to the base of oxygen and 1 to the base of carbon. If the base number is 1, it is erased and not written in the chemical formula. Therefore, the chemical formula for carbon dioxide is CO2, where the atoms have bonded in the ratio of 1 carbon to 2 oxygen atoms. This lesson will be continued with part 2. Check the description box for the link to the video on writing chemical formulae part 2.